In addition to the Opals experiment, there are a number of other experiments that will be going up on the SpaceX Dragon when it launches, and one of them was developed by the Merck Research Laboratories in New Jersey. That one will focus on crystallizing a human monoclonal antibody to advance the treatment of an immunological disorder. And we talked earlier this week with the principal investigator of the experiment, Paul Reichert. How did Merck get interested in this subject?
Well, let me give some antibodies or proteins which are produced by your immune system to target alien cells, bacteria, viruses, and proteins, which are foreign substances in your body. We actually are flying two monoclonal antibodies used in these experiments. Were engineered to target specific human proteins that have been found to be implicated in multiple human diseases.
Okay, so and this is an antibody that you were already studying here on the ground, right?
Yes.
How's it different having a space-grown crystal of the antibody? How does that contribute to the work?
We at this time there have been only 6 human antibodies structured by a procedure called X-ray crystallography, which uses high-quality single crystals in order to derive the structure. Our hope is that microgravity, with the advantages of minimal sedimentation and convection currents, will allow us to grow crystals which diffract to high resolution in order to get a structure. The structure can be used to understand how the antibody binds to the target protein, as well as help us understand how to make safer and easier to take medications for our patients.
So is it likely that the higher quality crystals would be more effective or just better to study?
I think that primarily, initially, we're hoping that the structure will allow us to better understand how the antibody works and to how to formulate it to make a preparation that patients could take more easily, as well as increase the compliance, make it easier for patients to take it in a doctor's office rather than to get a constant infusion, is the way a lot of monoclonal antibodies are delivered today.
Okay, I see. Well, can you tell us how this will work on station? What do the astronauts actually do, or what is done from here on the ground?
Okay, we're setting up about 30 experiments for each one of the monoclonal antibodies, and basically we're bracketing the conditions which we know the crystals will grow on Earth, but also anticipating that crystallization processes and microgravity are often slower. Molecules move slower, which we are trying to take advantage of to get higher order crystals.
Okay. I know also that you've done a number of similar, maybe not similar, but crystal growth experiments on the space station before and on space shuttle missions as well. Were those precursors to this? Did you learn things there that led to this experiment?
Well, in my earlier experiments, I was investigating another biologic drug called alpha interferon. Alpha interferon has been approved as a therapeutic for like the last 18 years for hepatitis C infections. And our interest was to grow crystals for structure, formulation, and purification. Interestingly, in all the experiments we did, we could never predict what would give us the crystals that we're looking for. When we designed the experiments to get large single crystals, we often got showers of small crystals. And when we designed the experiments to get showers, we often got large single crystals. The crystals we got from space were larger in some experiments and more uniform crystalline suspensions than the ones we found in the comparable Earth experiments. We were able to get a better structure, and the protein after crystallization was purer than the same crystals dissolved in our Earth control experiments. These experiments were never straightforward. That's why I'm actually very curious to see what's going to happen on this SpaceX 3, to see if our experience with the monoclonal antibodies will be similar than what we found with alpha interferon.
And I guess that it's just the lack of gravity that helps with the growth of the crystal? Is that all that it is?
Actually, no. Actually, it's two things. One is it's the minimal gravitational effects, and these crystals are not the kind of crystals that most people are aware of. These are microscopic crystals, and they grow in solutions. So they're actually in water solutions, and they actually bob in the solution. So the advantage in space is that these crystals, rather than drop in the solution due to gravity, they stay suspended, and they can be fed protein from all different sides, and that's how you get large single crystals.
Okay.
The second effect is the actual temperature difference. On Earth, most people know that if you heat a solution, you get this swirling effect in the solution itself as you're trying to heat it up. This is convection currents that you get. But in microgravity, you get very, very uniform temperature gradients, which is a unique property to take advantage of that a lot of people haven't in the past. And I hope in the future is something that we're going to take advantage of.
Definitely sounds promising. So how long will this experiment take, and how long before you would have it back on the ground for study?
We are very fortunate in that our experiment's going to go in a stowage bag, which is going to end up on the U.S. National Laboratory, where the experiment will be activated and will remain there for the duration that the Dragon module is attached to the International Space Station. A day before the Dragon will be disconnected, our experiment will be deactivated and placed back on the Dragon module, where it will be hopefully parachute down in the Pacific Ocean, and within 2 days we'll pick up our experiment in California. So I think from the time that we're anticipating this would be around 30 days total time from the time after launch that we will get our experiment back. At that time, we will look at both our ground-based and flight experiments. We'll photograph the crystals. We'll do X-ray experiments to compare the quality within the crystals on both the ground and flight experiments. We'll also, hopefully, we'll get some information about the purity. And one of the things that I'm very interested in is seeing what the particle size distribution will be for drug delivery. I think we will probably be able to complete all these studies within 1 to 3 months.
Wow, that's very fast. Well, thank you so much for telling us about the study. We really appreciate it, and we hope to hear more in the future about how it goes.
All right. You're welcome.